Free electron models in crystals. One of the very first challenges in condensed matter system was to understand why in metals we can have conductivities which differ in 18 orders of magnitude. So understanding the conduction of electrons in metals was one of the first problems that were tackled by condensed matter system models. So in these first models, the electrons in the atoms, when considered in a solid, need to be divided in two subsets. The core electrons, the ones that are closer to the nuclei, and the valence electrons, which are the outer shell electrons, which usually can be easily ionized. So the Drude assumption was that in a solid, this valence electron will be found shared between the atoms, and these are the electrons that are going to conduct. Here we have, for instance, the case of sodium. The valence electron is the 3s1 electron. The other ones are the core electrons. We are going to discuss here two free electron models that were developed at the beginning of the 20th century. First, the Drude model, which is an extension of the kinetic theory of gases, and which considers electrons as classical particles. And the Sommerfeld model, which introduces the quantum nature of electrons, which are fermions, and then uses Fermi statistics, Fermi direct statistics to describe them. When using one model or the other, we introduce the values of the electrical resistivity that can be obtained by measurements. It is interesting to note that in the Drude model, the electron mean-free path, that means the distance that traveled by one electron before, in average, having been dispersed, having a collision with a potential. This mean-free path of the electrons in the Drude model is of the order of the interatomic distance, while in the Sommerfeld model, it is of the order of several cell parameters. And this will allow to see that we need really to move to the Sommerfeld model. In fact, when we consider the evolution of the resistance, here the relative resistance to the one at ambient temperature of a metal, we see that we tend to what is called this residual resistance ratio at 0 Kelvin, a value which is not zero. We have a resistivity even at 0 Kelvin, which and this value depends on the purity of the system. And this is what clearly shown that the impurities, that means additional atoms or also the lack of an atom, a vacancy in a metal, is an important parameter to understand its resistivity. And this is compatible with the mean-free path found in the Sommerfeld model, which is about some number of cell parameters, and this is what we can find as a concentration of impurities. We are going then to analyze some of the hypotheses and consequences of the Sommerfeld model. So here we have a metallic object, 1 kilogram of gold. We have a lot of electrons, and the first thing that we can see is that this is a finite object. So we need to consider that the electrons are in a potential well. And when we do this, we need to introduce periodic conditions or boundary conditions. So the periodic conditions, that is one of the ways of treating the problem, can be best appreciated in the following figure. We can see here that this is a Pac-Man game, and if we look to the Pac-Man that is moving, it can go out from the screen from one side and get inside the other side. And this is exactly what the periodic conditions says to the electrons to do. They are not limited by the boundaries. They when they arrive to the one limit, they come from the other. This avoids to have stationary waves and then to have propagating electrons. The consequence of this finiteness of the objects is that the states of the electron states that in the K space, in momentum space, is going to be discretized. So we don't have any value. We have discrete values for the states defined by Kx, Ky, and Kz. And in addition to this, as the electrons are fermions, we are going to fill these states progressively. And because the energy is proportional to K square, we will get at 0 Kelvin a Fermi surface. That means the last electronic states that are filled. So inside the Fermi surface, every state is filled at 0 Kelvin, and outside all states are empty. This can be seen in another way here. Here we have at in the left the Fermi sphere, and here we have what is called the dispersion curve, the dependence of energy with respect to momentum. And this is a parabola because the energy depends on K square, h square, K square divided by 2 times the mass of the electron. And then we fill all the states here until a maximum energy, which is the Fermi energy. And the associated wave vector, Kf, is the Fermi wave vector. So what will be the effect of the application of an electric field in a Fermi sea of electrons? This is what is done through the Lorentz force, which is going to change the kinetic energy of the electrons. So this force, it will be in a given direction, and it's going then to displace the full sphere, Fermi sphere, in that direction. This will be here it is really amplified. Normal usual electric fields just create a very slight displacement, but so the electrical conduction then will be due to this variation of the momentum due to the force, which is given by the Lorentz force expression as this formula here. And what we see is that something is wrong there. Because what's wrong with this? If time is very long, variation of momentum is going to be very, very important, and we will end up applying a small electric field with relativistic electrons. So what we need then, as we said, to resolve this problem is to introduce some friction, which is due to the collisions, to the mean free path of the electron, and which is due, as we had discussed it in the Sommerfeld model, to the interaction with impurities. Within this model, we can calculate the electronic density of states for systems of different dimensions. Two particular cases: for 0 dimensions, in which the density of states corresponds to what we find in an atom. That means discrete states. So it is delta, direct delta. Another particular case is the 2-dimensional case, in which the calculation leads to a constant density of states. And then for 3 dimensions, we have square root of energy dependence of the density of a state with energy, and the inverse of this square root for the case of 1 dimension here. We can calculate the specific heat of a metal, evaluating first the energy of the system, the energy per unit of mole or volume, and then the specific heat is just the derivative of this energy with respect to temperature. To determine the energy, then we need to make the sum in a continuous way, this integral of the energy, considering the density of states and the probability of finding a state given by the Fermi-Dirac statistics. Here in this graph, we have plot the density of states as a function of the energy, which is in three-dimensional, as we have seen, proportional to the square root of the energy. And then when we multiply this by the Fermi-Dirac statistics at 0 Kelvin, this will define a number of occupied states until the Fermi energy. So these here in states will be all occupied. Then when we increase temperature, some of these states are going to jump to higher energy due to the evolution of the Fermi Dirac distribution function, which it is symmetric around the Fermi energy. And this will lead to this area here that can be considered as triangular to shift to this area here symmetrically. The consequence will be that at this symmetry is obtained whatever the evolution of the density of a state with energy, the obtained specific heat variation as this derivative, that is the evolution of how the states jump from this side to this one, will be independent of the dimension, because it's a question of symmetry around this point. And we find at the end that the specific heat for metals in a solid, in a crystalline solid, is proportional to temperature. In ordinary metals, in addition to the contribution of the electrons to the specific heat, we need to consider also the contribution of phonons. This contribution is dependent on dimensionality, and for 3 dimensions, this contribution is proportional to the temperature to the power 3. In fact, the dimensionality appears here in the exponent. So we have, for as in any metal, these 2 contributions for the electron and phonon contributions. The phonon contribution is going to be dominant at high temperatures, but at low temperatures we need to consider both. Thanks to the calculation that can be done in the Sommerfeld model, one can then predict the value of the proportionality coefficient gamma, and this coefficient depends on the Fermi energy. And we can compare these to experiments, and here we have the specific heat divided by temperature with respect to T squared, that as we see here, just by taking the above expression and divided by temperature, this leads to a linear expression in which gamma is just the intercept with the y-axis. So we have a way here to compare experiments and theory. And this is, for instance, what is done here for the case of metal, which is potassium. And we see that the agreement is really good. And then we obtain this coefficient here, 2.08. So in this table, we have for a number of simple metals, the measured values of gamma compared with the predicted ones. We see that in some cases, for instance, silver, the agreement is excellent. But in other cases, for instance, rubidium here, there is some disagreement. So in order to cope with this, we can define modified mass, and this is something that is done very often in condensed matter, for a modified mass for the electron. So we are going to define what is called the thermal effective electron mass by taking this expression of gamma and introducing the value of the Fermi energy, which makes appear n divided by v, which is the density of electrons, and the mass of the electron. So this expression is finally proportionally to the mass of the electron. So we can just decide that due to the interaction of the electrons with the different potentials, we can correct the model and say that the inertial mass of the electron has been modified by these potentials. And then we can assimilate the measured gamma to the calculated value, but modifying the thermal mass. And then we get this relation between what will be gamma for a totally free electrons in a solid, and the measured gamma, which led us to cope or consider the information coming from the interaction of the electrons with the ion potentials.